Hello, everyone, and welcome again to the tinyML Trailblazer series, to the March edition. We are in March now. tinyML Trailblazers is the place where you're going to meet some very interesting people from the tinyML community, people who drive this community forward, people who are very passionate about tinyML, and effectively they're tinyML masterminds, people who started this many years ago, and now they have their success stories to share with us. And our today's guest, it's a very special guest. It's a Professor Marian Verhelst from Belgium. She's a professor at W Department of KU Leuven, and she's also a scientific director of IMEC. And from the tinyML perspective, Marian is on the board of directors of tinyML Foundation. And thank you, Marian, for your service to tinyML community, for your leadership there. Before we start, it is my pleasure to acknowledge our strategic partners. Those are the companies who are active members of tinyML community, and they provide their support in many ways. And the list is growing. So the current list is AUN Devices, ARM, DeepLight, HMPulse, EMSA, PhotoHub, Greenwave Technologies, Gravity Inc., HOTG, Imagimob, ITMIS, ClickerTech, Latent AI, Maxim Integrated, which is part of Analog Devices now, Micro AI, NXP, Prophecy, Qualcomm, Kixo, Reality AI, Renaissance, Rixon Technology, SAP, Seed Studio, SenseML, Sony Semiconductor Solution, ST Microelectronics, Stream Analyze, SynSense, and Sentient. So you can see a very diverse list of companies from all over the world, big companies, small companies, software, hardware, and we're very fortunate and very proud to have this community behind. Next announcement, we are super excited about our upcoming tinyML Summit. The summit is going to start in just 4 weeks. It's going to be in-person event. That's why we are super excited. There will be a lot of presentations and a lot of networking and exhibition at the summit. So you can go to the website to check it out. And I think there is still room to submit your nomination for the best product or best innovation award. And on Monday, March 28th, there will be a tinyML research symposium focusing on the fundamentals of tinyMLs and the academic future of tinyML. So the program is also on the website. So I encourage you to go there and check it out. And we hope to see many of you at the summit in person in 4 weeks. Our next edition of the series, the April edition, will be with Eric Pan. Eric Pan is going to represent our Asian community and his company and himself. He is a founder and CEO of Seed Studio. This is a company very active in the tinyML area, in the tinyML community. You've probably seen a lot of announcements from this company. So really looking forward to this presentation as well, this interview as well. Again, Eric is going to share his perspective with Chris. And you can register for this event now. And it's going to be on April 6th, also at 8 a.m. Pacific. Just to to bring to your attention that our communities are growing fast. I think we are going to be close to 9,000 members on meetups by the summit. The Lincoln community are growing also very fast. So if you're interested in being part of this community, just go to these links or QR codes and you can join them, and you're going to see a lot of information and announcements there. And also this presentation of this interview is going to be available on our tinyML YouTube channel this week. And the YouTube channel is also getting very, very popular with a lot of subscribers and tons of material there to view, so you can go there and also subscribe. At this point, let me introduce the host of the series. So Chris is a very well known in the tinyML community. And more broadly, he is very well known in the high tech and entrepreneur type of community here in the Bay Area. He's done a lot of work in this space, started from his days with TenSilica, and he was a founder and the CEO of TenSilica, and then later CTO, and then he moved on and started working in the tinyML space, and he was the CEO of Bubble Labs. That was a company that was successfully acquired by Cisco in 2020. And Chris has numerous awards and IEEE Fellow in 2015 for his groundbreaking work in the embedded space, in the microprocessor space. So he's been pioneering a lot of microarchitectures, including RISC and MIPS. So again, a lot of accomplishments, and we are super fortunate to have Chris as the host here. Thank you, Chris. And at this point, let me give the mic to you.
Right. Thank you, Evgeny. It's wonderful to be here again. And it's wonderful to have Marian as a guest. Marian is a professor at Fpgas at KU Leuven and scientific director of Imec. And her work focuses on a whole set of ideas in embedded machine learning and accelerators and hardware algorithm co-design and low power processing. She is really a representative of one of the fundamental supporting concepts of the tinyML community. In fact, in all engineering and science development, the academic wing that goes alongside of the industrial and applied wing of this fundamental movement. And I think that this series focuses on entrepreneurship, but we sometimes forget just how central the flow of ideas from the research community into industry is. You know, sometimes we simplistically think, oh, well, universities, they train some people and they publish some papers. And so we hire those people and we read those papers and we're good. Well, it's much more sophisticated and complex than that. And the flow of ideas, the inspiration of new directions to go with the technology is really centrally important to almost everything that happens in the tinyML community, as well as all of the other interesting information technologies. And we could have no better representative of this spirit, I think, than Marian. So welcome, Marian.
Okay, thank you, Chris, for the nice introduction.
I think people would love to start by hearing a bit about your journey. How did you get here? How did you decide to go into academia? How did you decide to study electronics? How did you decide to focus on these hardware, software, co-design and machine learning and ultra low power questions? And how did you choose what you would focus on?
Okay, yeah, I can give you a bit of a background here, and you'll see that a lot of things depend on kind of coincidence like they often do. But I grew up as a daughter of two engineers. My mom also was a professor, and I was never ever going to become a professor, but I did become an engineer. That was okay. After my engineering studies, I did a PhD in Belgium still, and then I moved to US, where I started working for Intel Labs in Oregon, in Portland. It was not yet related to embedded machine learning, or at least not initially, because I did my PhD on a wireless digital backend for ultra-wideband locationing. So it was a completely different thing. But when I moved to Intel Lab, I started my job there, I became the digital person in an analog design group, because the whole group was making wireless frontends at Intel. And I, as a digital person, I was doing digital calibration and digitally enhanced analog for these analog frontends, and initially using traditional techniques. But more and more, I started to use machine learning for this digital calibration. And then after a couple of years, having lived for a couple of years in US, we moved back to Belgium. I became a professor here in Belgium because an opportunity opened up, and I thought there was a chance I couldn't miss. And I kept doing machine learning, but no longer to calibrate wireless front ends, but now to really do sensor processing, sensor fusion, all kind of embedded sensor related workloads. So that's a bit how I ended up at the university and in this field, kind of, through a path going over wireless transceiver research.
So which are your favorite applications right now, where you're seeing the most interesting results or seeing the most novel applications of either low power microelectronics or machine learning? What are kind of those unexpected rewards from that combination that you're discovering?
Yeah, good question. I am very excited at places where kind of three things come together. On one hand, extreme resource scarcity, of course, at the really tinyML aspects where I care about every last millijoule and every bit in my memory, and I have to condense everything so much for cost and efficiency reasons. That's number one, and I really like that because then the different domains have to work together. The hardware person has to work with the tools person, has to work with the algorithm person, or they don't have a solution. The second thing I like is if the application really has to collect a diverse set of information. So not a single sensor, but combine information from different sensors. Because then definitely when it gets a bit more complex, machine learning shines because a human interpreter cannot easily detect the patterns anymore that you want to recognize. And then there's more complex things going on between all these different sensory streams that come in. And that is interesting because also more and more we see that there different types of machine learning start to pop up, not just the plain neural networks that everyone is well aware of now, but a combination of pattern recognition at the lowest layer where the neural networks work well, but on top of that, some reasoning across different sensors, reasoning even across time, using some probabilistic techniques, maybe some logic reasoning techniques. And really you see these neural networks be not just the machine learning technique, but become a component in a bigger machine learning system or AI system, you could say. So these are very intriguing things to me.
What are some of the types of sensors that you're working with that you think are underappreciated today, where you really are finding some interesting new kinds of data and therefore some interesting new kinds of patterns, either from a particular type of sensor or what is the specific combination of sensors that you think are giving some of the most interesting results?
Yeah, I think traditionally the machine learning field has worked mostly with images.
Yes.
Which, it's okay, but there is much more, right? Definitely if you go to the tiny space, I think you, Chris, especially, you know that a lot of information is available in audio. And if we now think about acoustics, you think about keyword spotting, speech recognition, but that's only a teeny tiny fraction of audio information. There is much more like environmental detection, source localization, source tracking. You can really understand a lot what's going on by only listening and not watching to something. And that requires like 100 times less power. So I think that is already recognized more and more, but maybe still a bit undervalued. And then if you go even one step further, I think there is also a lot of information in vibrations. So movement sensing, accelerometry and things like that. And that we can sense with even lower power. And I think also there, if we can combine audio with video and movements or vibrations, you can selectively power on the video only when the audio is not giving you enough information, and the audio only when the movement is not giving you enough information, and going to the cheap sensor when possible, and only scaling up to the expensive sensors if needed.
Yeah, I think that's very important. I think there's such a huge opportunity in these low bitrate sensors of various kinds, partly because they get at the kind of information which isn't intuitive to humans and therefore isn't naturally very well developed by conventional algorithms. But second, because you don't need a huge amount of compute necessarily to operate on, 100 sample per second kind of data rate, and therefore you can aspire to these very small, environmentally powered, wireless connected kinds of things that have truly local, truly autonomous intelligence, and that's really a lot of fun.
Yeah, I fully agree, and you can even think beyond the single sensor node, right? A different, maybe one node then doesn't have a lot of information anymore, but they can collaborate with other nodes and selectively share some information, not all because it's too expensive, but some information when they think it's of value.
Yeah. So I'm really interested in this idea of how do ideas proliferate out from the academic world? Now, some research ideas are pebbles dropped in a pond and there are no ripples. Some ideas are dropped in a pond and create tsunamis in the outer world. In your experience, what are the methods that you use or the methods that you think work best in creating these tsunamis of impact of your work and in general the impact of the academic research community on the wider set of practices in the industry? Yeah. How do you think about proliferating these ideas? What's the academic entrepreneurship of having impact?
Yeah. I'm heavily convinced that a good idea almost never comes out of the blue in the mind of one single person and then he talks about it and boom, everything changes. I think a good idea comes based, first of all, from a pool of many ideas, is then these are discussed and with many people kind of brought up at different venues, feedback comes, you improve your idea, you massage it and you talk about it with others, you collaborate upon it. And then it gets bigger and gets more and more traction and you can excite a bigger community to keep improving it, lifting the bottlenecks and so on. So as an academic person, I think we are so lucky that is our job, having crazy ideas, many ideas, giving a keynote where you drop some of these ideas, you see what sticks, you get feedback both from colleagues, but also from companies like, yes, this is a problem we're facing, or no, this is irrelevant, or you get so much feedback, which allows you to improve it over time and kind of get a bigger and bigger group of people enthusiastic about it, starting to work on it and actually make it happen. And that's really how I see the best things developing and getting really noticed and used.
Yes. One of the questions I always think is interesting is not the question about the successes, but the questions about the setbacks, the failures, the things that you explored and said, this is really not a good idea. And it sets you off in some new directions, sometimes very productive new directions. Do you have an example of a place where you really hit one of those brick walls or really found yourself off in some really difficult area that gave you an indication of how to turn left and go someplace interesting and new? Yeah.
When I started as a professor, I only had few students, but one of my best students I on stochastic computing. Stochastic computing, where you try to compute with bit errors and sequential streams of bits and so on. We thought it was a pretty cool domain, but it really turned out nowhere because just computing with less bits was more efficient and more accurate and lower power than this whole stochastic computing movement at that time. But what was interesting is the guy that worked on stochastic computing was a very, very clever guy, and he was just looking for a few benchmark cases to try it on, and he took a JPEG encoder, and he also took some other, at that time, exotic workload, which was a convolutional neural network layer. It wasn't popular at all, no one really knew it, but we needed some workloads to do approximate computing on. And he did it. He proved it was quite useless to do it there, but he got intrigued by this convolutional neural network layer and doing reduced precision computing on it. And that kind of led to our team being one of the first to try out 2-bit and 4-bit processors for neural network workloads. So it was a big success in hindsight, but the stochastic computing that we started with, it completely failed. My lab never did anything with it anymore. But I'm still happy we started it at the time.
That's good. There are so many people who've stumbled across, neural networks or something like it along the way, which has sort of indicated that there's sort of a fundamental idea here, and everything that's adjacent is an introduction to the potential power of this data-driven computing model. So I'm also interested in how you think about the larger challenge of working in technology and being a role model and helping to educate young people or bring young people, young women into this whole world of academic research and advanced information technology. Well, what is your passion there, and what are some of the things that you're doing in education with young women, with people who are sort of discovering where their passions are going to be?
Yeah, I'm extremely passionate about enthusing young people for technology and engineering in general. One, because we would like to have a more diverse workforce, and we like to have more people just active in this area, but also because I think it is undervalued or underappreciated as a career path in some communities, like female people. What you see is that many people kind of doubt to start studying engineering because they feel that they want to have an impact on the life of others. They want to contribute to society. They want to do something for the good and not just for profit. And on average, and by no means I want to put stereotypes, on average, girls have even more that tendency than boys, of course, although both of them have it. And engineering is often seen as a job that does not contribute to society, that does not help other people. And I completely disagree. Of course, a doctor is a hero because he saves or she saves the life of people. An engineer is a hero as well because the machine, the cancer machine that was used by this doctor, that's designed by engineers, and their machine can help millions or thousands and millions of people. But that link is very hidden. Youngsters don't see the link between, as an engineer, I can make the society or the future better. And that's something that drives me to really do some outreach, to explicitly talk about this link and how we can contribute to society by studying mathematics, technology, and so on. So yeah, I lead a couple initiatives in Belgium mostly to kind of spread that message.
Great. I'm really interested in your view about emerging technologies. What do you see on the horizon? What are the technologies that you think may have significant impact in the tinyML community and through that on the real world in what gets used on a daily basis, whether that's new software technologies or new machine architectures or new sensor types? What do you see that's kind of out there just appearing out of the mist?
Yeah.
That could be worth paying a lot of attention to.
What really excites me recently is the thought that in the tinyML space, you would like to customize much more than we do today. And today we have rather standardized compute platforms, and we hook up a sensor through a standardized interface, and I write some code for it on a kind of general purpose programming platform or in tool flow. But tinyML, it's all about indeed grabbing this last bit of energy and millijoules and compressing it, doing everything as efficiently as possible, meaning that I want to customize my platform, my algorithms, my sensor collection as much as possible to the application at hand, to the environment where the system has to operate and so on. The only problem is customization is possible. I can make a customized C with a custom interface and a custom tool stack. You could do it, but not in tinyML because it's too expensive. tinyML also needs very fast time to market, very low cost solutions. So this low cost, fast time to market, and desire to customize, it seems like a fundamental bottleneck. But I don't think it has to. We can find clever solutions, and we can talk a bit more about how later. Maybe we can find clever solutions to do rapid customization towards application domains or problems at hand, but at the same time do it in a short time, and with a customized tool stack to make it easy to the developer or the user. A big part of that will also boil down, or a big challenge there will also be in the software and the tools community, like making compilers that can quickly customize to new accelerator architectures or combinations of accelerators. On one hand, hiding this for the application developers, of course, but on the other hand, not hiding it so much that you cannot exploit the hardware specificity of these accelerators anymore. And that's an interesting field, I think, where again, hardware people have to come together with tool developers and application people.
Yeah, it's really part of this fundamental tension that exists at the foundation of the electronic universe between optimality and flexibility. That in so many ways, we know how to build highly programmable, terribly inefficient systems. We also we know how, with a problem is exactly defined, how we could build a circuit that computes just that. But in between, we're full of these trade-offs. And there seems to be a, kind of inverse relationship between how much flexibility you get and how much, compute per watt or per dollar you get. And so much of what we're trying to do to make progress is somehow shift that whole curve so that we can get more of both. What do you see as the technologies that can give us a better combination, a better, if you will, flexibility, optimality product, as people try to get both, because you need both efficiency and flexibility in these platforms?
I think it boils down to, it's a bit immature ideas I'm going to talk about now, but I think it boils down to not seeing flexibility as something that necessarily will come as an overhead. You could also think of it as configurability. So I don't need a fully software programmable general purpose platform to be flexible. I can also make a platform that has some configurability options, which allow me not at runtime and every single cycle, but at basically either at deployment time or at very intermittent, very sparse moments in time, reconfigure my platform for specific sensor combinations or for a specific workload I want to run. And if you drive this to the extreme, but that's a very idea, you could even start to think of, instead of taping out chips, taping out small chiplets. And a small chiplet can contain some customized accelerator core. And depending on my application, I put together a different combination of chiplets or a different number of chiplets. People are already doing this, but in a high performance compute space, people are doing that. Maybe we can bring some of these ideas to tinyML to do not runtime, but keep some deployment time or fabrication or post-fabrication time, I should say, configurability, customization opportunities, without having to do a custom chip design for every single thing that you want to make, because that's of course infeasible.
Yeah, it's very true that there's sort of a whole set of circumstances where you don't know everything about the application, but you know a lot. You know that you're not going to your IoT subsystem is not going to wake up one morning and decide, oh, I want to be an enterprise storage subsystem. Or my application is not going to wake up one day and just say, I'm going to be a distributed operating system. It's going to do a range of different things, and anticipating what dimensions of flexibility you need, and more importantly, what dimensions of flexibility you don't need, is critically important to that, finding all the flexibility that's required and not 1 gram more flexibility than is plausibly required.
Yeah, and then of course it boils down to having the right set of tools to allow you to derive what flexibility do I need given my constraints and circumstances? And then two, once I've decided that, to very quickly have custom compilers and schedulers and so on for this selection that you did.
I want to highlight that we're getting ready to start taking questions. So if you start entering your questions on the Q&A tab, I think that would be really good to, so we can get the most out of Marian's visit with some good questions. One of the hypothetical wireless IoT structures that I think everyone imagines is that we ought to be able to have systems which are scavenging power and communicating over some ultra low power wireless network, at least locally in some sort of a mesh system. What do you see in this kind of deep learning, smart dust sort of area where you really have these self-contained subsystems, sensor and compute and communication and storage rolled together? What are the kinds of applications, and what do you think are the bottleneck technologies that keep us from being able to deploy these deep learning, tinyML, smart dust kinds of applications?
Yeah, I think the challenge, obviously, if you think about the smart dust concept, is, yeah, on one hand, every dot hardly has any energy. Indeed, there's scavenging energy, which means energy becomes dynamically available, and sometimes it's not available. So that's, I think, one very interesting aspect is this dynamic, dynamic resource availability, which require you to have more adaptive techniques. You cannot upfront decide who will do what. Some runtime allocation of tasks and work. The other side, of course, is that every dot will, again, hardly have any memory and compute resources. So they will naturally have to collaborate to get things done. And then you enter into this space of federated learning, adaptive approaches of what data is shared with who, depending on what task is running on what node, some kind of dynamic services that are running on top. Which, again, I think interesting is that when the whole stack comes together, like some of my colleagues are doing research on whether someone that uses a sensor node, does he have to be an owner of the sensor node? Can you think of a service model where sensor nodes are deployed by one company and other companies can virtually deploy different queries, analyses, whatever they want to do on these nodes, and hence have kind of virtual containers distributed over many nodes where they can get access to some data but don't have security issues with other people working on the same node, and so on. Again, it becomes an extremely interesting problem where you get hardware, software, virtualization, security issues all coming together in this field.
So the IoT did decide one day to wake up and become a distributed operating system. There is, a really interesting question that you raised there. We sort of think of, big, virtualized runtime environments as being sort of the domain of big computers, at least, something the size of your phone is sort of the one of the almost the minimum standard for doing that kind of isolated compute. What do you see happening in terms of the software that's necessary at a runtime to be able to do really interesting things, particularly with your model of flexibility? When you think about what are the minimum services that you want to have in one of these IoT computing nodes, especially if there is some sharing of information or sharing of compute resources, what direction do you think we go with that kind of software layer?
Okay, now you're entering a domain where I'm not the expert, I have to say. I'm more a hardware person than
I'm not the expert either, which is why I'm asking.
Definitely not an OS person, but yeah, obviously these nodes are running some operating systems where they now no longer have to just make sure their tasks on their own node are working, but they have to interface with other nodes and need some runtime control and synchronization between the nodes at the network level. But I'm not the expert there. So yeah.
Let's go in a different direction. There's been a lot of talk and some really fascinating positive results in the analog ML space. And clearly the appeal there is that you can do an awful lot of good work at relatively low resolution. And the analog equivalent of multiplication can be extremely inexpensive from a pure energy standpoint. But it also has some challenges because for the most part, we live in a digital world and incorporating that kind of analog compute into digital communications or digital resource management can be tricky. What do you see as the prospects and the strengths of analog approaches in the computational layer, not just in the sensing?
Yeah, we have worked quite a lot on that in our lab. What's undeniable is that you can indeed do more cheap compute in the analog domain than in the digital domain, at least if you stay at lower precision levels, 8 bits or let's say less than 8 bits. It's not the multiplication, to be honest, that people benefit most of, but it's the accumulation. So the addition is very expensive in digital because you need quite some accumulation bits, 24 or so. And in analog, that can be done cheaper. It has to be said that it comes with noise, so you don't get perfect computation anymore. But to some extent, neural networks can be trained to be insensitive to that. Now, of course, the problem, you cannot say like hooray and start to celebrate when you have your analog accumulator, because indeed it has to fit in a bigger system and the data comes in. Even if the data comes in the analog domain and you can immediately compute with it, it's very difficult to make analog storage. An analog bit cell or the equivalent of a flip-flop or a memory in analog is hard to build unless you start to work with capacitors, but then it quickly leaks away and so on. So in any computation where you need multiple layers of communication with some storage in between, it's hard to constantly stay in the analog domain. Some people try it, but for really, really small problems, you can do it. But if you come to a decent sized network, it doesn't. So typically, at least after the first layer, you have to go to the digital domain, which boils down to putting analog to digital conversions. And that comes at a certain cost, definitely because the output of this analog to digital converter then typically goes into a traditional memory, a buffer to buffer between the data of different neural network layers, for example. And what we then see is that it is great that I made this digital accumulation now in the analog domain, saved me a factor 100 or more of power. But if I now start to add my analog to digital converters, my activation feature buffer memory, you hardly see the difference anymore. So for energy reasons, in-memory compute or analog compute, it's not going to make a humongous difference, or it can make a difference, but not a factor 100. Maybe a factor 10 if you design everything super good. But it can still make a humongous difference for throughput reasons. Because what happens is that this analog compute is very, very, very compact. If you can live with the precision losses, you can really do thousands of more, or maybe a factor 1,000 more operations per square millimeter. And this allows you to get tremendous throughput speed ups. Even taking into account these ADC conversions and going back to the memory and so on, you really still get a very big benefit there. But don't underestimate the precision consequences. Designing high precision analog is difficult, and not all neural networks can cope fully with these losses in precision.
Great. We're starting to get some really interesting questions coming in. Dale asks, how do you look at the trade-off of computing locally versus transmitting data to a node with more compute, more energy? What's the greatest motivator for computing locally?
So I think there's a couple motivators. Let's start from the energy point of view. There is obviously the trade-off between, is it more expensive to process my data in my node, or is it more expensive to use this energy to send the data somewhere else? And that depends on the volume of data, but definitely for video and so on, you cannot send all the data out continuously, not only for energy, but also for bandwidth reasons. So energy can be a first driver. It depends a bit on how far you have to communicate. Second one is latency. Communicating, typically, that's definitely, if you have a large volume of data, it takes time. Some actions like robotic interactions or drone navigation and so on, they suffer from latency, and extra latency. And a third reason is privacy. Some people don't want certain data to leave a node, and then you have to compute locally.
We also have the question, can you say a few words about the Diana product that you just launched? What applications do you see for it?
Yeah, so Diana is the chip, is a chip that we presented at ISSCC last week, which has in one system on chip, it houses a RISC-V host processor, a digital AI accelerator, and an analog AI or an in-memory AI accelerator core. It was developed together with KU Leuven and Imec. So it tries to exploit these high throughput benefits from in-memory compute, as I just said, but it keeps also the digital accelerator for the layers that really need better precision. Typically, the first and the last layer of the neural net, for example, we run in digital because you otherwise lose information, but many of the middle layers we can run in lower precision in the analog domain. Now, it's not a product. I'm an academic professor. This is a prototype. But yeah, everyone interested in it, feel free to either look at our paper or send me an email.
Okay, we have a question from Rajiv. Can you comment on the state of spiking neural network and applications to edge IoT, especially with respect to data sparsity? When do you think the digital version of these products will be a hit market for tinyML?
It's a good question and a difficult one for me to answer. I am not actively working in spiking neural nets. I have been eyeballing them since the start of my career already for quite some time to see what's happening, what's coming up, and a lot is happening in that domain. It has many benefits in the sense that if you have a spiking sensor, which is a sensor that works more event-based and only sends data if something interesting is happening, let's say, then of course it's interesting that I can also process in this event-based fashion, that I don't have to reevaluate a complete neural network every frame, even if the input data is the same as the output, as the previous frame. So spiking nets try to do that. And kind of propagate spike information through the network, only update where something changed. The field, though, hasn't really proven hasn't proven that it's completely beats neural networks, even in these kind of applications, mostly because there are still some accuracy issues. It's much more difficult to train spiking nets than to train traditional neural networks. And also what you see is that, of course, the neural network, the classical ANN, traditional neural network domain, is, of course, also to a certain extent evolving from the other direction into this event-based operation where we now have dynamic neural networks, which also only update fraction of the network, or hierarchical neural networks. So also you kind of see their growth each other. The spiking nets kind of start to borrow training techniques from the classical nets to overcome their accuracy issues, and the classical nets, let's say, start to have more dynamicness, attention mechanisms, and so on, to kind of get that event-based nature coming in. And I think they're just more and more converging towards each other. Whether we will see spiking neural network commercial tools or commercial products on the market soon, yes, I definitely think so. Like with Profis and so on, you already have spiking sensors. More and more people are making spiking backends for it. but probably not the complete product will be a spiking product. I think it will always be used in a tandem where you might have a spiking front end to interface directly with the spiking sensor. And if that one detects interesting patterns, it might wake up a more traditional backend where some other networks can run at higher precision and so on. So I think a combination will be interesting, and many companies are thinking that direction and are close to having interesting things.
Great. There's a comment and a question from Stefan, who's working on his PhD thesis in the area of efficiency, flexibility trade-offs. But the tools are quite tricky, he says. An attempt to make universal enough tools can eat any amount of resources in development. And still every new customer will likely mean dedicated work for customers' specific demands. So what would be the right approach for making great tools for tinyML or for IoT in general?
Yeah, very good question. The tools issue is not easy. Also in my lab, we make a lot of chips, and then after you make the chip, you realize you need a compiler and a scheduler and so on, and it's not easy. But I'm very hopeful because in the field of tinyML, ML in general, but also tinyML, we see a big proliferation of open source tools, people making reusable tool stacks. If you think about things like TVM and MLIR, the related movement of MLIR, people really make tools that allow to more quickly either do code migration from one platform to another, or even completely customized compiler tool stacks, or make it easier to customize them rapidly. We're not there yet. If you want to plug in a new accelerator into such a stack, it still is a lot of manual work. But more and more we see, we see that people have dialects and so on that make it easier to do that. I also think going forward that we might see hardware designers taking this tools issues more into account when they design the hardware and not see it as an afterthought. It's not I first make an accelerator and a computer and then let's think about the compiler. But if I make my accelerator, how should I define its instruction set, synchronization mechanisms, data movement, primitives, and so on to make it easier to compile to this system. But that's a more long-term path.
There's a question from Raj. Do you think that energy associated with moving data from memory to processor is now exceeding the energy associated with the compute itself?
Definitely, without any doubt. I don't have to think about that. It's very clearly in many of our systems. And yeah, that is because in machine learning, you can typically compute at pretty low precision, and your compute energy goes down quadratically with precision, memory energy only linearly with precision, and it just quickly starts to dominate. The good thing about machine learning workload is there is typically quite a lot of data reuse. So I fetch from memory once and I can use the data a lot of times, but modern neural networks have less data reuse than the old ones, like AlexNet, massive data reuse. If you look at SqueezeNet or MobileNet or even more recent things, the networks are more lean, the networks are more elegant, perfect from a software point of view, but for a hardware designer, I lose a lot of data reuse opportunities. And it again pushes more efforts or more bottlenecks to the memory and the fetching of data.
Yeah, sort of the implication is that data reuse is a little bit redundant computation, such that if you really get good at optimizing, you remove the redundancy and suddenly you find yourself with less data reuse.
Yeah, indeed.
Nazaren asks, what is the biggest bottleneck in Diana? When you look at the applications, where are you kind of squeezed?
For Diana, I think there is a couple things that are still bottlenecks or could still be improved. On one hand, the analog is imprecise compute. which means that you have to train your neural networks to deal with that. And how imprecise it is depends on a lot of parameters that are even layer dependent, because it depends on how many rows and columns, or especially rows, in my analog compute matrix I'm using. And building this all into your training framework and training procedures is a bit of pain. We're used to digital, where the compute does what you expect it to do, and it's kind of a mind switch there. The second part is, again, the data movement. Diana is for IoT systems, so it has lots of small memories, both small local memories close to the accelerator, and then a bit bigger memory shared with the RISC processor and the other accelerator. And you constantly have to think what data has to go where, do the correct tiling to, of course, move the data as little as possible. But doing that is really, it's a complete scheduling optimization you do of what compute do I do when, and where is my data, and what data layout am I using. And making a compiler that takes that into account and optimizes that is also still a bottleneck at the moment that we're looking into.
Yeah, I mean, it's one of those classic cases where you know that local memories are more efficient than caches, but local memories rather than caches means a lot of software management of data location, and it becomes potentially a big headache. And inefficient when done wrong, and highly efficient when done right. It's kind of a steep cliff in terms of
it makes a lot of
knowledge and efficiency. Mm-hmm.
Yeah, indeed, exactly.
We also have a question. How do you think about the development of emerging semiconductor devices that can help build neural network more efficiently? Devices like memristors. Do you think it is the right time now to introduce these quite new devices into neural network practice?
Yeah, so it depends a bit what you want to use them for. So in the past, many people said we have to use these emerging devices because they will give us so much more energy efficient compute and so on. A bit related to the comment I gave earlier about in-memory compute, I don't believe they're gonna be a big game changer for energy efficiency, because the energy efficiency of your core is not determined by the core compute in this small in-memory compute device. It's peanuts compared to the whole system energy efficiency. What emerging devices can help for is, on one hand, again, density, compute density. I want to have as much compute per second per millimeter square of silicon. Well, many of these emerging memories are very compact memories, much more compact than some other devices we can find nowadays. Definitely there are scaled versions. So if you have enough parallelism in your network, which is also not always the case, we just talked about this data reuse thing, but if I have enough data reuse, I can build more compact compute structures with emerging devices. Could be interesting for some workloads. The other aspect, of course, is that many emerging devices are non-volatile, and they can allow me to store a lot of network weights non-volatilely, and then wake my system up and immediately start to compute. And also, of course, in tinyML, there are certain benefits to be able to do that, but only if I can store my complete network in my non-volatile array. I don't want to swap in and out of weights at that moment, because writing into these non-volatiles is very energy expensive. So if I can have such dense memory or such small network that they completely fit my non-volatile array, I can power up my system, compute with it, I'm done. Then I also think they have an interesting place in the design space.
Yeah, great. Mario asks, can you comment on the use of FPGAs as a tool in this search for the right flexibility, optimality combination?
Yeah, FPGAs obviously give you good flexibility, but you pay the energy price. An FPGA is not low power. If you could customize the system itself with an ASIC or buying a customized ASIC or making one, it will be order of magnitude lower power. But of course, an FPGA is good for rapid prototyping, or in many systems like camera systems or even security cameras, often an FPGA is already present in the system because they use it for camera calibration and that pixel removal and so on. Yeah, then obviously it's interesting. You can plug your machine learning system in there as well, or to very quickly have rather customized solutions. It's also good, but if you really care about energy, the efficiency of the FPGA will hurt you. It can give relatively good throughput still.
That's great. I think we're getting very close to the top of the hour.
Yeah.
So thank you very much. It's great. And I'm sure that if people have additional questions, we'll find a way to funnel questions to you.
Feel free to reach out to me.
To get answers. But it's been delightful to chat.
Yeah, I enjoyed. Thank you for the interaction.
Thank you, Marian.
Yes.
Thank you, Chris. It's been an amazing hour. I think it just flew. So at the end, I'm going to ask my favorite question, Marian. So this is supposed to be Success Stories series. What is success for you? What does it mean for you? How do you define success?
Oh,
You personally.
you catch me with a difficult last question. I am a very collaborative person. So I am happy when I see that ideas that I have thrive and are picked up by others and we can work on it together. And of course, as a professor, I'm most proud of my researchers, my students, and if they have ideas and I can help them to push that into the world and be successful with these ideas, then I'm happy. That's my success.
That's a great answer. Definitely you have a lot of successful students and we know some of them. So I think from this perspective, you're a very successful professor and person and researcher. And thank you again for joining us today.
Thank you.
And at the end, let me just acknowledge our sponsors again. It's the list is here. And also let me do it one by one for the executive. It's ARM. It's a technology foundation for tinyML, HMPulse, leading HML platform, Qualcomm, advancing AI research to make efficient AI ambiguous, Sentient, energy efficient tinyML, Platinum sponsors, DeepLight, they use AI to make other AI faster, smaller, and more power efficient, ClickerTech as a global IoT solution company, Reality AI, they're adding advanced sensing to your product with HAI tinyML. Renaissance has a broad portfolio of edge computing devices. And the gold partners are PhotoHub, Maxim integrated part of analog devices, Legend AI, they develop adaptive AI for the intelligent edge, Micro AI, NXP, Seed Studio, and again, Eric is going to be here in a month. SenseML, they build smart IoT sensor devices from data. ST Microelectronics, SynSense, and this is the list of silver partners: AON Devices, AMD, Greenwave, Grovity, HOTG, Imagimo, ITMIS, Prophecy, Kixo, Ericsson Technology, SAP, and Stream Analyze. And again, we hope to see you in a month. I think it's going to be a very interesting perspective of the Asian market and Asian technologies and kind of Asian startup, a very successful startup. And Eric Pan, founder and CEO of Seed Studio, is going to be here with Chris on April 6th. Well, thank you again, and we have a good day or night, and we hope to see you in a month at the next April edition. Thank you. And thank you, Chris and Marian. It's been great.
Thank you, Evgeny. Thank you all.